Okay, so we finished last class talking about this minimax approximation, and if you had a chance to look at doing this for e to the x, okay, I think it was on the interval minus 1, 1. Okay, so if you took a look at kind of the working this out in the book, what did you have to do? You had to look at the error, and then you said we want to try to minimize the error, so we set the derivative equal to 0. That's not so hard. Then you've got to try to solve for x. Now you've got some candidates for your minimizer, and you got to kind of check them and decide which one gives you the minimizer. Okay, which you can do for this example. It's maybe not that straightforward to generalize this approach, though, right? It's actually quite a lot of work just for this simple example. Even the process of taking the derivative, setting it to 0, solving for x. Well, you can do that with very simple functions. If you have complicated functions, maybe that's not straightforward. You have to compare a whole bunch of things and, again, try to solve some different equations, which you can do for this simple example. For more complicated things, again, maybe it's not that straightforward. Maybe it doesn't generalize that well. So there's an alternate approach for function approximation that's probably more commonly used. Sometimes maybe this is what you want to do. But as an alternate approach, we might try to not minimize the maximum error, but minimize some other measure of the error that's easier to work with. So what we're going to talk about instead is, let's look for a least squares approximation. Okay, so in other words, what do we try to do? Say we're doing polynomial approximation, although you might want to use something other than polynomials. Let's try to find some sort of polynomial, okay, that instead of minimizing the maximum error, it's going to minimize to an L2 error. So where we take the error and square it, and we're not taking the maximum of this now, but we're doing an integral. Or a sum, depending on whether you're looking at the discrete or continuous case. What's that? So inner products are going to become important in a few minutes, exactly. So we're trying to minimize this now. F minus Q, say, where we take Q as polynomials of degree, again, less than or equal to n. And now we're not doing a maximum norm, but we're doing a 2 norm. Okay, or what we'd often do, minimizing some positive quantity is the same as minimizing the square of that quantity. And that's often easier, so we might also do this, which will have the same solution. So the 2 norm squared. So we're going to see that this problem is actually a lot easier to solve. I'll give you a little intuition into why it should be easier to solve. So if we try to think intuitively about what's going on, let's say I'm interested in some function, f minus q. And maybe my function f minus q looks like this. So it might have a corner. Well, now I say, okay, what I'm actually going to look at is not f minus q, but in some sense, f minus q squared if I'm doing an L2 norm, right? Doing an L2 norm, I square whatever I'm working with, and then integrate it. Well, what happens when I square this? When I square this, all of a sudden I smooth things out. And smooth things are going to be easier to minimize, right? So if I think about, the simplest thing you might want to do for minimizing, take the gradient and set it equal to 0. Well, in this case, I can do it. I can take a gradient and I can set it equal to 0. Over here, I can't take a derivative at the minimum, right? The derivative doesn't actually exist. So your usual tools that you want to use for optimization are going to tend to work a lot better here. L2 is in some sense a smoother. Now, let's compare that to what happens when we're using not a squared type of distance, an L2 type of distance, but a maximum type of distance, which we did before. So again, let me take some choices of f minus q. This time I want to take the maximum of them. So maybe this is one of my f minus q's, and maybe this is another one of my f minus q's. Okay, and this time they're nice. I actually started with something smooth. But now, if you think about what happens when I take the maximum of these two things, well, the maximum is going to follow this curve for a while. And then all of a sudden, it's going to switch over to this other curve, and there's going to be a corner right here. Right, so we've got here a corner. This is the maximum of f minus q1 and f minus q2. And so somehow this maximum norm is not a smoother, it's like a desmoother. It took things that were beautiful and smooth, like maybe these were infinitely differentiable, and it introduced a corner where there is no derivative. And again, as soon as we start introducing corners, non-smoothness, it becomes harder to do the optimization. It becomes harder to take derivatives and set them equal to 0. So we could think of this maximum measure as a desmoother. Okay, so let's see what actually happens when we try to do this least squares minimization. We'll see if we can work out something that will actually generalize really nicely, so that if you have a different function you want to work with, or a different set of basis functions that you're interested in, you can still work this out really quickly. But that's what we want, something that's easy to generalize that you could code up and have your computer solve this quickly. So let's look for it. Let's do this generally. Let's look for an approximation of this form. Okay, so we start with a function, whatever it is, and I want to represent it in terms of some simple basis functions. Okay, so I'll call my basis functions Vj. These guys, again, these are my basis functions. Okay, and it could be some polynomial basis, or it might be some other basis that you think represents what you want to do. Okay, and now we're given some data points, say, and we want to try to come up with a representation. In other words, come up with the coefficients that will try to keep this approximation as close as possible to our function, or as close as possible to the values of the function that we've actually been given. So let's say we're given m data points. Okay, this doesn't have to be the same now as the number of basis functions that I'm using. Right? When we were doing interpolation, everything had to match up. Now that's not the case. So we're given our data points, xi and yi. And now what we're typically going to assume, like I said, these numbers don't have to match up. And in fact, we're going to typically assume the number of data points we have is larger than the number of basis functions, right? And that's reasonable based on what we've seen before when we did interpolation. If we used low degree polynomials, we might get good results. If we used very high degree polynomials, all of a sudden you're building lots of oscillations into things. So it's actually reasonable, very reasonable, that the number of data points may be rather larger than the number of basis functions. And that's also good from the other point of view, that we want a simple representation, something that is kind of cheap to store, right? Cheap to work with and manipulate. And that means ideally we want this n to be relatively small. We don't want to be storing more information than we need or manipulating more than we need. Okay, so what do we want? We want that yi is approximately equal to now, not exactly equal to like when we did interpolation, this representation when we plug in our data points. Okay, now these phi's are known, right? We pick our basis functions, whatever they are. The xi are data points that are known. So these are just some numbers that we know. And these a's are going to be our unknowns. So I can certainly write this as a matrix vector product, so similar to what we've done before. So I can represent this as something like a matrix capital Phi times a vector A. Right here, phi ij is going to be phi j at xi. And A is going to be the coefficients here. Okay, and now this is not a square matrix, right? You know, we did interpolation, and we think of it this way. And we'd have a vector here on the other side, and we'd just say, okay, we could invert this matrix. Now we can't do that. It's not a square matrix. It's not invertible. So this, what do we really have here? This is an m by n plus 1 matrix times an n plus 1 by 1 vector. So if I look at this matrix vector equation, this is actually overdetermined. I have more equations than I have unknowns, so I can't expect to be able to solve this equation. Right? The best I can hope for is to try to approximately solve it. So that's what we're going to do. We're going to try to approximately solve it, not in a way that minimizes the maximum possible error, but in a way that tries to minimize this L2 error. Okay, so let's try to find the coefficients that minimize this L2 error. Call the error E as a function of A. So different coefficients give me different results. We want to find the coefficients that minimize this. And we're going to look at now y minus phi times A in the L2 norm. Okay, and I'm going to square it because, again, minimizing the L2 norm is equivalent to minimizing the square of it. But again, squaring things, like the picture we saw here, squaring things smooths things out and it makes life easier. We can take derivatives much more easily. Okay, so if I write out the L2 norm squared. Okay, so remember, whatever's in here is a vector, right? So if I want to compute the L2 norm of a vector, what do? I dot its components together and add them up, right? So that's the same as saying, let's take this transpose times itself, right? This becomes a row vector. This becomes a column vector. And when we multiply them out, they're going to add the components together, multiply the components together, and then add them up. And if we multiply this out, what do I have? I have y transpose times y. I have, okay, a y transpose phi a, that's just a number. I also have a transpose phi transpose times y, that's the same number. The multiplication is done in reverse, but it's the same number. So what do I really have? I have 2 a transpose phi transpose times y, and then a transpose, so when I multiply this together, a transpose phi transpose times phi times a. Okay, so this, right, E of A is just a number, it's the error, right? When we do all this, we get just a scalar number coming out. So this is a function of multiple variables, because A is a vector, but it's a single valued function. And we want to minimize it, that's our goal. So how do we minimize this?
Solve for phi.
Okay, so phi is known. We know phi, right? What are we trying to solve for? We're trying to solve for these coefficients, right? Phi are our basis functions, they're given.
If in a way you could make the middle term probably kind of 0 or something.
You want to sort of make the middle term 0. Let's be more precise. How do I minimize? Okay, let's say it's a function of one variable. How would you minimize it?
If that vector were perfect orthogonal.
Okay, you're thinking orthogonality. Take the derivative and set it equal to 0. Like, that's our standard approach for minimizing things. Okay, now that's not a standard derivative, it's a gradient, right? But it's going to be the same deal. If I have some sort of surface, right, and I want to minimize it, at the base here I have not a tangent line, but a tangent plane that's completely flat. So my tangent plane is going to have gradient 0. So we need to set the gradient of this equal to 0 to find the minimum. Okay, so let's work this out. This term doesn't depend on A, so there's nothing to do here. This term depends on A. It's linear in A, right? So this is, it's basically A times something. Okay, so it's going to follow our usual rules for taking the derivative or the gradient of a linear function. It just means that term goes away. And we're left with its coefficients. Okay, and this, right, this is now not a number, it's a vector, but that's what we expected. We're computing a gradient. We expect to get a vector coming out. All right, so this was linear. This is a quadratic term in A. And this is a perfectly symmetric quadratic term in A. So again, this is going to feel like exactly what you do in the scalar case where we have an A squared, right? And the 2 comes down. And what do we get? This is when we get an A 2. So we had an A squared, the 2 comes down. We keep our constant here. And we still have an A left. Okay, and again, this works because this is a symmetric quadratic form. Okay. If you don't believe it, you can go home and sit down and write. No, like seriously, if you don't believe this, sit down and write out precisely what the components of this would be, and take the different partial derivatives, right? And you'll see that it's coming out. And it's a good exercise if you don't believe this. But this is what we want to set equal to 0. Okay, so what do we want? We need to solve the minimizer A satisfies, okay, phi transpose phi A equals phi transpose times y. Okay, now if we were doing interpolation, we would have been back here, right? We would have had a phi times a equals y, which we said we can't solve that here. That's overdetermined. So you still see that floating around here. You still see the phi times a and the y here. But now this whole equation that was ill-posed before, right, has now been left multiplied by this extra matrix. So what do I have here? Now I do have a square matrix, right? So this, this we have the potential to be able to solve now. So this is indeed now, what did I say phi was before? Phi was m by n plus 1. So this is n plus 1 by m by n plus 1. So this is an n plus 1 by n plus 1 matrix. All right, A, we said, had n plus 1 components. Okay, and now this is also going to have n plus 1 components. All right, so this was n plus 1 by m. This was m by 1. So together, this is going to be n plus 1 by 1. This is now all of a sudden a reasonable matrix vector system to solve. So this equation here, this is called the normal equations. Yeah.
Is that it as in normal to the surface?
As in normal to the surface, no, I think you're overthinking that. Right, and you can see interpolation in there. You can see that if we were in a special case where actually the number of data points was equal to the number of basis functions, right, and that this was actually a square matrix, it would actually reduce to ordinary interpolation. But now it's more general. Now I don't have to have the same number of basis functions as data points. And what else? This was easier, right, than the minimax approximation, where you had derivatives, and then you solve some sort of nonlinear equation to find the maximum, and had a bunch of candidates that you had to work with. Here, things were beautiful and smooth. It was just a quadratic. Quadratics are easy to work with. If you're going to minimize something, you'd love it to be a quadratic, because that's the easiest thing you could possibly minimize. So we could write out really an explicit expression for what the coefficients have to be in terms of just a matrix vector solve. We okay there? Are we happy with this is what the coefficients that we want? Okay, we can do this also when we're approximating an entire function. So we might have just data points, or we might really know the complete function, and we just want to come up with a simple representation of it or a simple approximation of it. So we can try to do this with the entire function. Okay, so what are we trying to do? We're going to try to minimize. Okay, again, I have an E of A. Okay, which is now not data values, but the entire function minus my representation of the function in terms of these basis functions. And now we're doing an integral here, right? So if I want to work out what this is, this means I'm integrating over whatever my domain is. So let's say we're doing this from A to B. And then what do I have? I take what's in here, I square it, and that's my L2 norm squared. Okay, and now I want to do the same thing. I want to minimize this. That means I should be taking a gradient of this and setting it equal to 0. Okay, it's a gradient with respect to these AJs. And that's great, right? Even though this is sitting inside of an integral, the AJ The AJs you could pull out, if I expand this, I could pull the AJs outside of the integral, right? We're integrating over x. We're not integrating over the AJs. So if I want to, say, take partial derivatives of this with respect to AI, what do? I just take a derivative as normal. I say, okay, I bring the 2 down. Okay, and then I want to take the derivative with respect to AI of this inner part. Okay, derivative with respect to A naught. The derivative with respect to AI of A naught is 0. With respect to A1 is 0, right? The only one that gives me a non-zero term is when the AI actually shows up in here. So then, again, that's minus AI times phi. So I pull out a phi. Okay, and again, I can write this as I'm trying to solve for these coefficients. I can write this as a system of linear equations for my AIs. So if I rearrange this, the normal equations now are going to be, well, let's, yeah.
Is that the phi stays inside of the integral?
The phi is still inside of the integral, that's right.
Okay.
And that's important, right? This quantity over here doesn't depend on x at all, right? It just depends on, it's a vector of things that depend on a. So we wouldn't want to have a result at the end of the day that depends on x. So just as a little sanity check. If there's no x's at the beginning and there are x's at the end, then you've done something wrong. Okay, so if I rearrange this, I'm going to do exactly what I did here. Bring everything that involves a to one side of the equation, and everything that doesn't involve a to the other. What do I have? I have AJs. Again, the AJs don't depend on x, so I can pull them outside of the integral, times the integral of phi, Vj. Okay, and then what's left on the right-hand side, I have an integral of phi times f of x. That's what we did. We took the partial derivatives, right? We set them equal to 0, and setting the ith partial derivative equals to 0 gives me an equation in I, right? So we have, again, a bunch of these equations. These are from I going from 1 to m.
That is like a kind of an inner product.
It looks like an inner product, exactly.
That's what I was saying.
Set of without no eigenfunction.
Without a what?
Looks like a set of without no eigenfunction.
Well, you're thinking orthogonality. We're not quite to orthogonality, but yeah, that's important here. I haven't assumed anything about them being orthogonal yet, though, right? Okay, so again, I get a system of equations for my A's. I think this is I equals 1 to, I switched the role of I and j here.
There you have a formula for the coefficients. You just divide through.
And now we have we don't just quite divide through. This is still a matrix vector system, right? Because each of the equations involves all of the A's. This is still a matrix vector system, but it is a linear system, right? This is aj times some number, which you can compute, but you sum over all the j's. So this is a matrix vector system still, which is a good point. I'm going to come back to that point in 2 minutes. How can we make this easy to solve? Right, and we saw when we did interpolation, right? Okay, we got a matrix vector system for the coefficients, for example, the van der Waals system. That's great. You can solve that in principle, but maybe it's not so easy in practice. So that's an important point we'll want, is how can we make this easy to solve? Yeah.
So we had m data points. Did we lose m completely in this equation, or?
So here, So here we don't have data points, right? So in this example, we had data points, right? y1, y2, up to yn. In this example, we can think of it as infinitely many data points, right? So we have actually the entire function here. Okay, and then sometimes you want to tweak your concept of L2 a little bit. I'm going to mention that here. We're going to come back to that a little bit later. But we can also do a weighted L2. A weighted L2 norm. So here, what do? We let W be some sort of non-negative weight function. Okay, and what it might tell you is that there are some areas of the domain where you maybe care more about matching your function than others. Maybe you know there's going to be issues near the boundary. You want to assign more weight near the boundary. We'll see that we get some interesting results with different weight functions. But you can think of this as saying how important or unimportant relatively are things going on in different regions. Okay, and here, then the goal is to minimize now. Okay, basically the same thing. Now we just have this W in front of it. And then our usual AJ, phi j of x, all squared. Okay, and when you do the minimization, the normal equations will look exactly like this, but now with a W sitting inside of all of your integrals. So now the normal equations are going to be same deal over all the AJs. And the only difference is you get this W coming inside of here. Okay, same right-hand side, but again with this extra weight function.
Question.
Yes?
This is like how Rayleigh quotients and stuff like that are, well, that is derived, right?
How the Rayleigh quotient is derived?
Yeah, it's like, it looks a little similar, right?
Yeah, you're going to see similar things there, exactly. So these kind of concepts, you're seeing inner products here, you're thinking ahead to orthogonality. Those are important in lots of different problems, and you can see this as you take different classes. The same concept is going to emerge over and over again in different contexts. Okay, so good things have happened so far using L2 in that we can come up with a really simple system of equations for the coefficients, which we couldn't do when we were trying to minimize a max norm, an L infinity norm. Right? That was hard. Now, our next question is, great, we've got a simple system of linear equations. Simple in that it's a linear system. But we know that linear systems are not all created equal. Some of them are really easy to solve. If this matrix happens to be the identity, then life is good, right? You've got the solution written down in front of you. If this matrix happens to be the van der Waals matrix, well, we're not so happy, right? So that was very poorly conditioned. And okay, you can throw it into a linear solver, but the solution you get back might be nonsense. So what freedom do we have here? Well, we have some freedom over choosing the basis that we're going to use. So we want to try to pick basis functions that will lead to a system that is nice, that is easy to solve. So yeah, I feel you're already thinking ahead to what kind of basis you want. Let's just think to an equation like this. We're trying to solve an equation of the form m times a is equal to some right-hand side. And we've done examples like this, which are easy or not easy. I think we did an example maybe on the first day of class for a 2x2 matrix where we said the residual looks small, but the error is bad. So what happened there? Do you guys remember?
The matrix was close to non-singular.
It was close to non-singular. In other words, right, we're trying to find the intersection of two lines, and those lines were nearly parallel, right? So this this would be bad. If our basis functions were somehow nearly parallel, this would be bad. On the other hand, we knew that if the rows were completely orthogonal to each other, for example, if we had, again, the easiest thing in the world would be to have the identity matrix here, right? And that means the rows are completely orthogonal to each other. This would be good. Okay, so indeed, a few people have suggested we'd like a basis that's orthogonal. So what does orthogonal mean? It means that most of these terms here are 0, right? And that would be great, right? If we had, for each one of these equations, one of these terms was 1 and all the rest were 0, that would be the easiest thing in the world, right? If, when I put in, for a particular I here, all of them were 0, except when I had an I here, that would mean I could read off what AI is. So that's exactly what we want. Like, why solve a complicated linear system if we can find a way to build a linear system where we have to invert the identity? You know, I'll invert the identity all day, no problem. Okay, so life is easy, life is good. Things are easy if our basis is orthogonal. Okay, and by orthogonal, I mean just what I said, that most of these integrals are going to be 0. Okay, so we're going to say a basis is orthogonal with respect to this weight function. So with respect to the weight function w, if this integral, so phi I times phi j, is equal 0 whenever I is not equal to j. Okay, if that's the case, again, almost all of these terms are 0 except, so we're summing over all the j's. All of these are 0 except when j is equal to I. So then I get ai times this integral with j equals I. And I can read off straight away what my ai is. And so in that case, ai is going to be equal to, okay, the integral of phi I squared divided by the integral of phi I times f. Oops. Let's try it the other way around. The integral of phi I against f divided by phi I squared. Yep. With respect to. Okay, and in shorthand notation, if we define an inner product, or a dot product, okay, so if we define the inner product to be a way of combining two functions to get a number, and the way is going to be to simply integrate these two, the product of these two things against this, whatever our weight is. Okay, we get an inner product. This gives us a concept of a norm. So if I take the inner product of f with itself, now all of a sudden I'm getting some kind of measure of how big f is. Okay, this induces a norm. Okay, so we're going to say that the norm of f is going to be the square root of the inner product with itself. Right, which is now the square root of this integral of f squared. Okay, and now we can say, okay, a basis is orthogonal if the inner product of two different basis functions is equal to 0 whenever they're not equal to each other. So a basis is orthogonal if, right, the inner product of phi I and phi j is 0 when these are not equal. We can also talk about an orthonormal basis. Okay, if it's equal to 1, yeah, if the norm of these basis functions is equal to 1. So if it's both orthogonal and the norm of all of these basis functions is equal to 1. If the, so with respect to whatever weight function you're using. It's not saying the weight function is 1. It's saying that this quantity here in the denominator is 1. Okay. So in other words, the inner product of phi with itself. The inner product of phi with itself comes from doing this integral. That's right. You integrate phi squared against this weight function, you get 1.
Is this a induced norm?
It's
Is it helpful to think of it as an L2 norm? Or
it's like a weighted L2 norm, exactly.
weighted L2? Okay. Would it be appropriate to put a 2 when we write our homework and stuff near to the norm, or?
Do you want to put a 2 here? So it's a weighted L2 norm. You might do like a W or something if you want it to be really clear. Say that this is the new norm induced by this weight function W. If you've got different norms floating around, then you've got to label them. If there's just one and it's clear from the context, then it doesn't matter. Okay, and then the important thing is, if the basis is orthogonal, then we can solve for our coefficients right away, right? It's just the inner product of phi I with f divided by the inner product of phi with itself, or in other words, the norm of phi squared. Okay, so it's nice compact notation, and it's compact notation that works actually at the continuous level. It works if you have different weight functions. It also works at the discrete level. So if we go back to where we have data, finitely many data points, you can still describe a normal inner product there, a normal just dot product. So all of this is the same at the discrete level.
So now that we found those coefficients, Professor,
Yeah.
does it mean that when we go back into our representation of the error of the function that we want to approximate, now we say, okay, this representation is the minimizer.
Yes, so we can say now we've solved for the minimizer. Now we go back to our error function and we can say this choice of AI is the one that minimizes that error, absolutely. Right, and what's nice is you can write it down explicitly. It's very simple to write down. Okay, all of this still holds for a discrete case. Yep.
I have a follow-up to this question. Does any of this prove that the error goes to 0?
Does this prove that the error goes to 0? No, we haven't said anything about the error being 0. We've said this minimizes the error. Right. So if you give me a choice of basis functions, you say these are the basis functions I'm willing to use. I'm telling you this is the best you can do with that choice of basis function. It does not mean that f of x can exactly be represented by that. Now, if you have a set of basis functions that's somehow complete, then, if you think of monomial basis functions, for example, which are not orthogonal, some orthogonal polynomial basis, right? And if f, say, has a Taylor series representation, right, then you could say, well, as n goes to infinity, as I include more basis functions, then I hope that this representation converges to f. But no, this is not a proof of that. This is just saying what's the best we can do given these basis functions. Yes?
Is this weight function unique, or you can choose it?
You can choose the weight functions. So this will hold these definitions, this concept of orthogonality. This choice of the coefficients that minimize will work for any weight function.
So does it going to change your A?
It will change your A's, yes. Different weight functions will give you different A's. So the idea here is that you might say, I care about the error more at some places than at other places. I care what happens. Maybe this region is really important in my domain, and this region is less important. So I'm going to assign more weight here and kind of penalize the error more here. So the coefficients are going to say, let's try to match the function values better here, and maybe we don't do as good a job out here. So the different weights will give you different coefficients. What is the way to choose the W? We're going to talk about some different W's today and also in the next lecture.
Probably we will discuss later. There are conditions on W. I mean, if is integral must be equal to 1 or something.
There are there are conditions on W. So I think I said W should be non-negative. Certainly, it should be integrable. So yeah, I'm assuming W is nice enough that it's integrable. It's not actually critical here that its integral is equal to 1 because what's actually going to come up is this ratio here. So the scaling doesn't matter so much, but certainly it should be integrable. Yeah, Jake.
Do we ever try to our error is dependent on the set of basis functions?
Our error is dependent.
Minimize that over spaces of basis functions?
So would we try to minimize our error over the spaces of basis functions? So I'll say maybe you want to be clever in your choice of basis functions. So I mean, most of what we've done so far is polynomial basis functions, but we're going to talk about other things when we talk about periodic functions. Maybe polynomials aren't the best thing, right? And you want to use periodic basis functions. So yes, in that sense, you'll try to be clever and use basis functions that actually are reasonable for what you're trying to do. Am I going to solve a big optimization function where I say, hey, let's look at the space of all possible bases for representing a continuous function or whatever? Well, no, I'm not going to do that big optimization problem. But yes, we are going to try to be clever. Okay, so this representation still holds at the discrete level. So if you want to solve your normal equations, okay, we get the same solution of the normal equations if you have orthogonal basis. With now your inner product is going to be represented this way. Right? These are vectors now, not entire functions. So now you're just going to be adding up. Right? You're just going to be doing a standard dot product.
And if we have a weight, just...
All right, and if you have a weight, you can throw it in there, sure. Okay? And then, now the notation is the same, right? You use the same representation of your coefficients. Just now, how you compute your inner product is different. Okay, so we want orthogonal basis functions. That means, okay, that sounds nice in theory, right? We know if we have orthogonal basis functions, normal equations are easy to solve. And now we have to decide, is it actually easy to come up with orthogonal basis functions, right? That's another important question. This is easy under the assumption that these orthogonal basis functions are actually kind of easy to find.
Well, like you mentioned it when, at one point that, okay, if we have monomial, they are not orthogonal, but then again, we can make them to be orthogonal and orthonormal if we use the Gram-Schmidt process.
The Gram-Schmidt process. So that's exactly what we're going to do, and I'm not going to go through it in a ton of detail because I think you've seen it before, and it is in your book, but I will just highlight what's going to happen.
So for the monomial, we will get Legendre polynomial.
That's right. For the monomial, we'd get Legendre polynomials. We'll write down the first few of them right now. Okay, so we can construct. So you give me a basis, whatever basis you like. Maybe it's the monomial basis or some other basis. So we can construct an orthogonal basis via the Gram-Schmidt process. So what's the idea of Gram-Schmidt? Again, I'm not going to go to it in tons of detail, because I think you've seen this before. Well, the idea is maybe you started with these basis functions, C0 and C1, and they're certainly not orthogonal. So we say we want to make them orthogonal. So what I'm going to do, I'm going to start by just picking one and saying, all right, I pick you to be my first basis function. Keep you. Now this guy I need to fix a little bit. So what am I going to do? I'm going to project him down onto C0. I'm going to say I can represent this guy in terms of one component that lies in the direction of C0 and another component that lies orthogonal to it. I throw out this component. It doesn't have any new information. It's just more of C0, and I keep this orthogonal part. Okay, and this becomes my phi1. And then you do that on repeat, right? Maybe you give me a third basis function, and I say, well, he's not orthogonal to the other guys, but I'm going to break him down, and I'm going to project him onto phi0, and subtract off that component. I project him onto phi1. I subtract off that component. Whatever else is left, that's what I keep as my new basis function. Now I've subtracted off all the parts that lie along phi0 and phi1. Whatever is left is orthogonal to the rest. So this is in your book. I'm going to do a quick example, but again, I don't want to spend a ton of time on this process because I think most of you have done this before. Yeah.
Can we do Gram-Schmidt for functions as well?
You can do Gram-Schmidt for functions, yeah. So all you need a concept of orthogonality. That's all you need. And we have that for functions. We have that for functions with weighted inner products or kind of traditional L2 inner product.
Any function can be represented as a vector.
What's that?
Any function can be represented in vector.
Any function can be represented in vector form. How do you mean? Talk about it later? Okay. I'll do an example. We're going to actually look at these Legendre polynomials. Okay, so let's do a simple example. We were interested in polynomials. Okay, so let's say I start with this basis. Start with my monomial basis. Okay, so I have C0 is 1, C1 is x, C2 is x squared, and so on. And we've seen that these are certainly not orthogonal, right? We built, when we tried to do interpolation, we got a matrix, which was certainly not the identity matrix, which we would get for orthogonal polynomials, or something like the identity matrix, something diagonal. We got the Vandermonde matrix, which was highly unpleasant. So let's see if we can orthogonalize them. We're going to work with the simple weight here of 1. and I'm going to look on the domain -1 to 1. Okay, so I start by saying I just need a starting point. So my starting point is going to be just the first guy, right? And he's just sitting there pointing out into space somewhere, and there's no one to compare him to, so I don't have to worry about orthogonality yet. So I start with phi naught equals 1. Okay, now what do I want? I want to compute my next one. So I'm going to start with this. I want this guy has the new information that I want, the fact that I can go from constant to linear. So he has that information that I want, but it's not necessarily all new information. So what I've got to do is work out this projection and subtract off that projection, right? So that I'm only picking up this component.
You're taking the integral and change the second function so that it's equal to 0.
Yeah, so what am I going to do? I'm going to project. So I'm going to take the inner product of this with my phi naught, right? Divide out the norm squared, yep. And then I'm going to, so that's how much of this guy I'm subtracting off. Okay, so we work this out, and what is this? This is now an integral of x dx of 1 squared dx okay, yeah, and indeed, in this case, right, this is an odd function over the symmetric interval. So this is 0. So in fact, 1 and x were already orthogonal to each other. Now that's not going to continue to be the case as I bring in new basis functions. The process is the same, so we'll do maybe one or two more. Yeah.
So we're doing the L2 norm, it should be the absolute values, right? Because we want it to be summable. If we're doing
Sorry, what should be the absolute values?
the integrals of the absolute values of the function. Otherwise, we could get like zeros in our denominator. I don't think it changed anything.
Right, so
Or if we're squaring it, I guess it doesn't matter.
right, so we shouldn't get, so we're looking at the original function we had. We started with the basis functions, right? That means if you just took the function 0, and that doesn't point anywhere, that gives me no information to go in space. That's not a basis function, right? So I'm not going to get a 0 in the denominator. Either way, and yeah, again, I'm doing an integral of something squared. So if it's positive some places and negative some places, right? Like this guy, I'm not going to be integrating x in the denominator. I'd be integrating x and then squaring it. Yes, so we shouldn't have to worry about zeros in the denominator.
That is an interesting question, though, right? What you're saying is you'll never get an odd function in the denominator?
We're not going to be integrating an odd function in the denominator, and that's because, right, we're looking at the norm, right, the L2 norm. The L2 norm says I take the thing and I square it, right? I make it always positive, so it can't be odd. It could certainly be even, yeah.
This is a formality, and when we're saying on -1 to 1, are we saying that we're defining the weight function to be 1 there and 0 otherwise?
You could think of it that way, that I'm defining the weight function to be 1 there and 0 otherwise. I'm trying to do function approximation on this bounded domain. If you want to go unbounded, then, and this is maybe more to Francesco's earlier point, you have to be careful in that everything actually is going to be integral. So your weight functions, your basis functions had better be square integrable. So that you could do, but you have to be careful what space of functions you're looking in there. All right, let's do maybe one more. Phi2 is equal to, okay, so now we want to bring in the information from x squared. Okay, So we're going to do what we did before. Okay, so we go to take off these inner products. So we're going to do an inner product of x squared times 1 divided by 1 squared. Okay, and then now we've got to do the same thing for the newest basis function that we came up with. Yeah, this is times 1. So we're going to subtract off some multiple of this newest basis function. So now we're going to do here inner product of x squared with phi 1. Okay, and then I've got to divide by the norm of phi 1 squared. So that's, I take x and I square it. Okay, so if I work this out, what do I have? I have an x squared. Here I get, I think, a 1/3 when I work it out. This is an odd function here, so that's going to be 0. Okay, and that's what I'm left with. And you can keep going, right? Same procedure, right? So my new function, inner product of my new function with all of my previous basis functions, divide by the norm squared of my previous basis function, and make sure to include my old basis functions out here that I'm subtracting off. I don't want to just subtract off a number. I want to subtract off a component that lies along this old basis function. Oh, yep.
So now if we just take those phi 0, phi 1, and phi 2 so far, we will see that they are orthonormal. So if we take the inner product, let's say, of phi 0 and phi 1, we will have a 0. But if we take the, let's say, the norm of phi 1, we will have a 1 because it's wait a minute. Yes, it is orthonormal.
So they're not orthonormal.
No, orthonormal.
They are orthogonal. Yeah. So if I now if I integrate this against this, we'll get a 0. You know, if I integrate this against this, we'll get a 0. You can actually see that if I multiply this out, I'm gonna get an odd function exactly. Yeah.
Just to check, since they happen to be the same, in this case, the inner product is with the new basis function, and the thing in front is the old basis.
The inner product, right? So let me write this out in one more step. So this is my x squared, my new basis function, minus, and what am I doing? So this was phi naught of x out front. Then I have the inner product of phi naught with the new thing I'm adding in, divided by the norm of phi naught squared. And then I do the same thing with phi 1. So the inner product of my new function against phi 1 divided by the norm of phi 1 squared.
Just wasn't sure because the phis and the psis are the same for the first.
Yeah, the phi, that won't always happen, but yeah, in this case, the phis and the psis are the
so
same.
I wasn't sure
Yeah.
which thing you were taking.
Nope, it's great clarification. And again, you know, the general procedure is written out here too. And I think most of you have seen this before. It's just a matter of, you know, refreshing your memory and you'll have it again. But this, you know, this intuitively is what I'm trying to do. I'm doing this projection. Saying how much of this lies along here? I subtract off that number times C naught. There is freedom, so somebody pointed out these are not orthonormal. Oh, indeed, there's freedom to scale these basis functions in different ways, right? So I could have a 1 and an x here, and the integral of that product would be 0. But I could also make this a 5 times x, right? And they'd still be orthogonal to each other. So there is freedom to scale things here. Traditional way of normalizing these ones is to multiply them by a constant Okay, so that phi of 1 is equal to 1. Okay, if you rescale them that way, you get, okay, well, phi naught is 1. Phi 1 of x is still x. Phi 2 now gets rescaled a little bit. Where did he go? All right, so now if I plug in 1 right now, it's 2/3. So if I multiply that by a 3/2, I will get phi of 1 equals 1, and so on. The next one is 5x cubed minus 3x, and so on. How do we deal with other domains? You could do, there was nothing special about -1 to 1. It's just the domain that we picked here, right? But all that would change on a different domain is the limits of your integrals. I mean, you might not get this simple odd symmetry that you can take advantage of to simplify things, depending on the domain. But
You can also just take the basis we derived here and sort of translate it.
you can certainly rescale the basis here, yeah. Right, you do a change of variables in your integral to bring your integral from a to b back to -1 to 1. So you can certainly scale things that way.
Professor?
Yes.
Now, if we go to the beginning, when you were talking about the error using the least square problem, if we take the monomial basis,
Yes.
we have our function, given function, our domain, and then we try to find that error, minimize the error with the monomial basis.
Yep.
But now we do the same thing with this Legendre polynomial, so we will see that the error on this case will be better than the error.
So the question was, if we tried to minimize the error with the monomial basis versus minimizing the error with this new basis, will the error change? No, the error is the same. So we're still, say I go this far, I'm still representing cubic polynomials. And I can do it in terms of this basis, or I can do it in terms of this basis. The minimal error will be the same. What's different will be the coefficients. Okay, and the key difference is that with this basis, the coefficients are really hard to solve for accurately. But in principle, it can be done, right? In principle, it can be done, and it gives you the same minimal error. And here, we have a really simple formula for the coefficients, which again will give you the same minimal error, but with a lot less work, and probably less accumulation of rounding error, for example. This is known indeed as, these are the Legendre polynomials. And there's a closed form representation of these. So these can be written this way. As phi n of x equals, this is going to be highly non-obvious. Okay, and then the nth derivative of x squared minus 1 to the nth power. So that's highly non-obvious. It's written this way. But how would we check it? And one thing that is clear, hopefully, okay, this in here is an order 2n polynomial, right? I take n derivatives of it, and I get an order n polynomial. So these are order n, or degree n polynomials. It's a funny way of writing a degree n polynomial, but it is a degree n polynomial. Then if you want to make sure that we're recovering the same basis, what do we have to check? We have to check that these actually are also orthogonal. Okay, and then I guess the nice thing about this representation is it's actually not that hard to check that they're orthogonal. It's a funny looking representation, but we can do it with not too much work. So let's just notice a couple things about these derivatives. Say I take the jth derivative. Let's put this up here. I'm not going to write this out exactly, but what you are going to find is that basically this, every time you take a derivative, the power comes down and is reduced by 1. And then you have to multiply by derivative of stuff on the inside. So when I take j derivatives, I'm going to get something like f squared minus 1 to the n minus j times a bunch of stuff, right? As long as j is less than n, right? Obviously, once we've taken more than n derivatives, then that n goes away. And that means, in particular, if you plug in the endpoints, you know what happens, right? So if I want to plug in the endpoints to this, at x equals plus or minus 1, well, I don't really know all of the stuff that's in here, but I know that it's multiplied by 0. And boundary terms are important because when we check orthogonality, we're about to do an integral. And to simplify integrals, our main trick is integration by parts. Integration by parts means we need to evaluate things at the boundary. Okay, so let's check. It's not that hard of an exercise, actually. So let's check the orthogonality. Okay, so we're going to consider two basis functions with I not equal to j. And I'm just going to suppose they're ordered so that I is less than j, right? There's nothing wrong with that assumption. Okay, I have two basis functions, and one of them has a smaller index than the other one. I've decided to call that smaller index I and the bigger index j. Okay, I'm not making unfair assumptions here. If we want to do this inner product, okay, we've got to integrate those things against each other. I'm going to have some terms that don't depend on x that I can bring outside the integral. So I have 2 to the I plus j, I factorial, j factorial, and then my integral. So my integral is going to involve an ith derivative and a jth derivative. Okay, it's not obvious looking at this that this should be equal to 0, right? We need to do a little work to make that obvious. But we have a simple tool at our disposal, integration by parts, right? Whenever you see an integral and you want to simplify it, integration by parts is a great tool. Okay, so let's do some integration by parts. Okay, so I get my boundary term. So one of these terms stays the same. One of them I take an antiderivative of. So let's let this one stay the same. Let's actually not do that yet. This I take an antiderivative of. And that's easy because it's actually written as a perfect derivative, right? It's the jth derivative of something. I just have to pull off one of the derivatives. So we're going to take a j minus first derivative of it now, of x squared minus 1 to the j. And this happens at my limits. Okay, and then I have my remaining term. And now taking an antiderivative of one and another derivative of the other one. All right, so I add one more derivative to the first guy. And I take off the derivative of this guy. The boundary condition terms are 0, exactly. That was the argument that I made over here, right? That, okay, if the number of derivatives out here is less than this power, the boundary terms go to 0. And that's what I have right here. The number of derivatives is less than this power. So I don't know exactly what this is. I don't need to work it out. I know that it's going to start with an x squared minus 1. So this, indeed, at the boundary terms goes to 0. And now I'm going to keep playing the same game until I've moved a whole bunch of derivatives over to here. The boundary terms are going to keep being 0, so we're going to keep doing the very same game. Okay, so what do I get at the end? Well, I get a sign flip every time. So I'm going to have minus 1 to some power. If I move j derivatives, it'll be minus 1 to the jth power. Okay, all the boundary terms have become 0. If I've moved j derivatives onto here, okay, and I've taken away j derivatives from here. All right, now I can't move any more derivatives off of this guy, right? I've gone as far as I can go. There's no derivatives there anymore. And, okay, it's maybe not clear what's happening here. We can think about what's happening here. How many derivatives am I taking? I plus j. I made an assumption that I was less than j. So here we're taking, okay, j is bigger than I, so we're taking more than 2i derivatives. Right? Because j was bigger than I. This is a polynomial. What's the degree of this polynomial? 2i. What happens when I take a degree 2i polynomial and I take its derivative more than 2i times? I get 0. So this term becomes 0, and they are actually orthogonal. Yeah?
What do we mean by the 0th order derivative?
The 0th order derivative is just the function itself. So if I had a first derivative and I took one more derivative off of it, I'd be back to the function. Okay, so therefore, these are orthogonal, right? And that indicates that I've come up with an alternate representation of these Legendre polynomials, right? They're the correct polynomials, right? And the nth guy is an nth degree polynomial, and indeed they are orthogonal like we wanted. So it's another way to represent them, and we'll see a lot of that, where you can kind of go through crunching them, computing them by hand, or you can come up with general representations, which sometimes makes it a lot easier to prove general properties of your space of basis functions. So if I was just doing Gram-Schmidt over and over again, it would be hard for me to prove some general properties that all Legendre polynomials have. But if I have a closed form expression, okay, now I'm in business to maybe prove some general things. So I'm going to stop there, and then we're going to, from here, keep talking about some different weight functions that we might like, and some other basis functions besides polynomials. So